All right. Well, you can see me. Welcome back to Friday class. Yeah. So, a number of things I want to touch on before we jump in. You got an email from me the other day, maybe a day or two ago, just reminding you we have an exam coming up in a couple days. And I gave you some kind of bullet points as far as to what to start to expect there, and how we'll move forward with that. And I will give you more information here in the next day or so as well before I post the exam. But just to kind of rehash or so you have your head done square here. At some point Sunday evening probably I'll post it, if not early Monday morning. And so basically you'll have I want to give you a window of time, because I know while we do kind of have a time period on Monday, I know with a lot of this being distance or kind of hybrid learning, people's schedules are all over the place. So to allow you to remain flexible and get through all the other stuff in your lives, I'm going to give you this chunk of time. So, at least 36 hours or whatever that would be, or all of Monday and then part of Tuesday. So I think I had listed it'll be due Tuesday by like 5 p.m. But you can do it earlier, and it's not a 36-hour exam. It's designed to be, in that 60 to 90 minutes. And the benefit, I think, for you all is that there isn't that time crunch. Now, that can be a concern, especially if you're kind of a perfectionist. Because you could spend all day on it. But I'm not building it to take up a lot of time. I'm building it as a typical kind of what you would see as a in-person exam that takes the hour and a half of class period or something like that. I got a couple questions about kind of the structure, or I tried to lay out a little bit. I haven't finished writing it, so I don't know exactly how many questions are on it. But typically the way I design questions are kind of multi-part. So you may only see 5, 6, 7 questions, but each of them will likely have part A, part B, part C, and so on. And so oftentimes that's built around kind of one core story or concept, and I want to elicit multiple responses. So you might have part of that question say, calculate the variance of both of these sets of numbers, and then describe what that means. So that might be part A, and then part B might ask you to describe kind of what that means about the two groups of numbers. And then this is me trying to make up a question on the fly, but you can see there'd be multiple chances, and maybe even before part A there's just a talk about the why we might use the squared deviations instead of just deviations or something like that. Okay, so the whole exam is not going to be on standard deviation, but that might be a part of it. So what I'm trying to express is that there's going to be multiple parts. And the other thing I want to stress to you is that if you get bogged down in one part of that question, so say for instance you just can't figure out how to calculate the variance or whatever I'm asking you to, it doesn't necessarily mean that you have lost your way on the rest of it. And I'd like you to even if you can't do one calculation, try the rest, or answer as if you had. You can write things in, even tell me I couldn't quite figure this out, but if this were the case, then here's how I would interpret it. Okay, so I'm looking for, and I think I talk about this in the syllabus, that I'm looking to give partial credit because I'm interested in, even if you don't have the whole concept wrapped up, if you can show me that you're on the way to understanding it, that's important, because again, none of us, myself included, understand all of statistics the first time through. So I'm looking that you're on the journey and that you are attempting and trying and giving effort and showing some sign of grasping these difficult concepts. So yeah, and then the other thing to remember, and we talked about this again at the start of class, is that they're also not designed that you're going to necessarily, be able to crunch every answer and have everything pristine and perfect. And if you do get some things wrong, or you just couldn't quite get it right, that's okay, and it doesn't mean that you've failed this exam. Again, as I grade them, I'm taking into account how everybody is interpreting the questions. So sometimes I write questions that are not how I intended them. I've even messed up the numbers, and yeah. So, but then also, I'm taking into account the difficulty of the question as well. And so if in general, if the question was not either clear, or it was a more difficult question than I anticipated, that doesn't mean that everybody failed just because of the way I wrote questions. So bear that in mind if you get stressed during a part of the exam. And again, just to reiterate, the only way that can go badly for you is if you don't answer anything. So if you leave parts blank on the exam, I don't have any justification to give you partial credit. Okay, so give me something. Help me help you. You're too young for Jerry Maguire. Okay, so that's enough of a long blurb about something that you haven't even seen yet. But so as far as class goes, we are not going to hold class on Monday because many of you will be working on the exam, and that time period might be the best time for you to actually physically work on it. So we won't have class on Monday. So we will have class on Wednesday, and I will upload that video as I have been doing every week to make sure that so that kind of lecture material will be up on Wednesday. The other thing I want to just prepare you for is that there's a chance that I do Wednesday fully online as well. And the reason for that is that what may and most likely is food related. I had some nausea and vomiting last night. And so I think I can attribute it to some different food that I was eating. But in the state of the world that we're in right now, still working through what that means and if I should go get tested or whatnot. And so it may be as simple as we simply, because we weren't going to have class on Monday, we may just go online on Wednesday, and that'll kind of also make sure it's protecting all of you. So I'll make sure I let everybody know that probably via email early next week. But for a lot of you, that just means you're Zooming like normal anyway. I just might be here instead of in front of a whiteboard. Okay, so yeah. I'm trying to think if there's anything else that is not related to what we're going to talk about today. Related to what we're going to talk about, this exam will cover chapters 1 through 5. And I know we're just getting into chapter 5 material, but this is a good reason to, in all honesty, force you to really dig into chapter 5 for the exam. And I think that'll be good because this material sets up where we're headed for the next few chapters. And so it is important that we kind of have our heads wrapped around this material and feel comfortable using things like the permutation formula and the combination formula. So we're going to turn to that now. Yeah, and obviously if there's any questions, feel free. So I want to kind of pick up where we were on Monday or Wednesday. And just keep talking about some of these practice problems because I do think it's a good way to frame kind of what we're doing and why we're doing it. So we have a couple questions left on that sheet that I posted, or the Word document that I posted the other day, and I recently, just this morning, re-uploaded it, so it has another 2 questions on it, which I'll pull up on the screen here. But those are on the canvas now. If you still go back into the same one, the chapter 5 lecture questions, it has, I think, 2 more questions, 8 and 9. And so we'll get to that today too. So if you want to download them and look at it, or look at it later and go back and look at them, that's available. So I think we were, and it might vary a little bit on Monday and Wednesday. The Wednesday lecture should be up on Canvas. I think we were just kind of talking about ways we could order the colors of the rainbow, right? And I'm going to try to pull this up. That's not where I wanted to be. That's really small. See if we can get a better look at that. And we were using, again, this kind of silly example, but to talk about what we can do as far as permutations. Hopefully that's somewhat visual or visible. I know sometimes Zoom gets a little bogged down and it gets fuzzy, so we'll try to I'll just tell you what it says there. How many ways can we order the colors of the rainbow, right? And so we had talked about this at lecture, but let's kind of use this as a jumping off point to get back into this concept of permutations and then combinations. Let me get the cat hair off of the iPad. So we had talked, and this might vary depending on the lecture, but we had talked about ordering. There we go. So red, orange, yellow, green, blue, and purple. And how many different orders could we put these 6 in, right? And I think we talked about kind of one way to structure our thinking about it is if we, and again here in the first scenario we are concerned about the order, right? So these are 2 different. This is the first one and this is the second one, and these are different because we have flopped those last 2 colors. And that's really going to be the difference between permutations and combinations. So because we're talking about permutations, the order matters, and so these are counted as 2 separate ones. And we could keep going, right? Let's see, we could do blue, purple, green, and so on, right? And as we saw, this quickly is going to get out of hand, and we're going to run out of space. And part of that reason is that we have, again, one way to think about it is that in that first slot, how many can go in the first slot? Well, there's the ability to put 6 in there, right? Any of those 6 colors. In the second slot, now that we've chosen the first, we could put 5 different ones in there. Realized I don't have the chat open. Okay. And then continuing on, if we've chosen the first 2, there's then 4 options, 3 options, 2 options, and 1 option, right? And so in this scenario where we want to use all 6 colors, we have 6 times 5 times 4 and so on. And so that becomes mathematically 6 factorial. Right? I don't have to be this big, I can get out of the way. And so that's kind of the start of our permutations, and it will be the start of our combinations formula, right? And in this case, it's our answer, so 6 factorial, right? But the permutation, let me just write that up there. The permutation formula is more general. Okay, so we have n and r, where n is the number of objects. Here we have 6 colors, and r is the number we're choosing. And in this case, we're also choosing 6, right? We're not leaving any of the colors off. And so that becomes n factorial over n minus r factorial. Oops, put the bracket in the right spot. And so in our case, it's 6 factorial, and then because we're doing 6 minus 6, this becomes 6 factorial over 0 factorial. And if you haven't worked with factorials much, you may have forgotten, but 0 factorial is 1. Okay, and so that's kind of, it doesn't follow with the rest of them, right? It kind of, you'd think, all right, it means 0 times whatever. Anyway, it just becomes 1. And so we end up with 6 factorial over 1, or whatever that is. I think it's 720. See, that's 30, 120, 360. Yeah. So 7, I'm in the way. Put it over here. So we have 720 different orders we could put these 6 in. Now, when we talk about combinations, well, let me shift gears because this will be confusing if we do this. If we want to talk about, maybe we don't need all 6, right? So we may have just briefly touched on this in lecture, but if we only want to use 4, so red, orange, yellow, green, that's a set of 4 colors. So this is no longer applicable. Okay, so we only want to use 4 colors. Okay, so red, orange, yellow, green is 1. Red, orange, green, yellow is 1. Red, orange, green, blue. Right, that's a separate one. Now, how do we calculate the number of different orders we can have here? So, as we did before, one way to think about it, right? We could put 6 times 5. In the third slot, we would only have 4 options left, right? If we've already chosen red and orange, we have yellow, green, blue, and purple. So we have 4 options left. And then lastly, for the last slot, we have 3 options left. Okay, whatever 3 we haven't used. What we don't have anymore are those 2 last slots, right? So in the previous example, and actually we might be able to flip back. So red, orange, yellow, green is our first option here. In the previous example, we had 2 of those. Right? Both of these were red, orange, yellow, green, but we had 2 permutations that started off with those 4. So in this case, we only have 1. Okay, so you can start to see the difference in that we're going to have fewer options here because when we used all 6, we got 2 permutations out of that starting 4, and here we only get 1. And in using this mentality, we miss out on this 2 times 1, right? We've lost that in our calculation. So how do we mathematically, so using this logic, we can probably answer the question and say there's 360. But how do we mathematically represent that, and how do we keep it more general to do more complex questions? Well, if we want to lose the 2 times 1 here, right? We said before this was 6 factorial. How do we make 6 factorial equal to this? Well, what if, or maybe a better way to say it, I'm going to switch colors because this might be an easier way to conceptualize it. What I actually want now is to express 6 times 5 times 4 times 3. Right? That's the answer that we've come up with over here. There's 6 options, 5, 4, and 3. We don't have that 2 and 1. Okay, but we know we could express 6, 5, 4, 3, 2, 1 very easily as 6 factorial. So how do we do this? Well, we make this into a fraction, and let's multiply by 2 times 1 and also divide by 2 times 1. Right? Because these are going to cancel. So mathematically, all we're doing is multiplying and dividing by the same thing. Okay, and so this can lead us to easily write this down as 6 factorial over 2 factorial. So here again, much of what we're trying to do with these formulas is have them in an easily kind of generalizable form. But I want you to see kind of the connection as to why we're doing, I can't reach that high, why we're doing this form of it in place of just writing it all out. Okay, so we can think about 6 times 5 times 4 times 3 as 6 factorial over 2 factorial, right? Because if we write that all out, we can cancel out the 2 and the 1 from the numerator and the denominator. And so, just Let's get rid of that. Okay, and so putting it back to our NPR, never put that together before, National Public Radio, one permutation, I guess. N factorial, how do we get to 2 factorial, right? We need 2 factorial on the bottom. Well, 2 factorial is the number that we aren't using. That's the number of options we aren't using. So every time we write down 4 of these, we've left 2 off. Okay, so we can write that as n minus, so the total number we have minus the number we selected leaves us with those 2 that we're not using. Okay, and so that's all the permutation formula is doing. It's saying we have this many on top, and we just want to make sure that we're not counting these ones that we aren't using. So the n minus r is the ones we've left off. Okay, so in our case, that becomes 6 factorial over 2 factorial. And again, that's going to come out to 360. Okay. Right. So now the last transition I want to talk about is what does it mean when we switch to combinations, right? So in our example, we're talking about a rainbow, so we might want to display the colors in a certain order. But what if we are putting them into a paint can, right? And so we don't care what order, but we just want to know which of them are going in, right? And it's been a long time since 7th grade art, but I assume that might mean that this all becomes brown. But let's say it matters which 4 colors we put in there. And so in that case, we're switching gears and we're talking about a combination. Okay, and actually I'm going to put these back up. So this is just taken from the book, but notice how similar these 2 formulas are. Can't get my mouse on that, but that all the only change in this combination is that r factorial, right? And that's the number selected. And so that's going to allow us to deal with the fact that get out of there. Okay, that's going to allow us to deal with the fact that when dealing with permutations, these are different, but with combinations, they're the same. Okay, and so that's going to happen a number of times every time we write down all of these permutations, a certain amount of them are going to be doubling up. And it turns out that that's exactly the number of doubling ups is the number of, or the share that are doubled up is connected to the number of options we're choosing. Okay, and so all we have to do is include that last little, so again, it's n choose r, so that's the way we usually refer to it, as n choose r, in this case 6 choose 4. And so we have n factorial, we have the same n minus r factorial, but we take into account the fact that some of them are going to be doubled up by dividing by r factorial, right? And in this case, r factorial is going to be 4 factorial. Oops, that's not helpful. I don't need to rewrite that. So we will have 6 factorial over 4 factorial over 2 factorial, right? So now, word of warning, if you haven't played around with factorials much, you can't multiply these together. So this is not the same as 8 factorial on the bottom, right? This does not work. So because, again, we have to view them as 4 times 3 times 2 times 1 times 2 times 1. And so just be careful that you don't try to shorten things up too quickly. And so let's ignore that. What we actually get is, we can cancel out and say, 6 factorial divided by 4 factorial is just going to leave us with 6 times 5 over 2 factorial, which is 6 times 5 over 2, right? Because that 4, 3, 2, 1 is going to cancel out the top 4, 3, 2, 1. So we are left with 15 different combinations. If I could draw a 5, 15 different combinations of 4 colors each. Okay, so vastly different than the 720. I might have even said it's going to be 320. I don't know what I was doing. Maybe that was the other permutation. So 15 is much different than 320. I think that's where we're at. 360. Disregard all the numbers I've just said. They're probably not right. 15 is much different than the 360 in terms of permutations of 4 colors. Okay, so we'll come back to this, yeah, we'll come back to this concept of permutations and combinations in a little bit, but I do want to turn our attention to Bayesian theory, and my computer is starting to run very slow, so if I'm choppy, I apologize. Is that running? Okay, so this is a question that's on the new version. Let me pull it up because I know some of you won't have it there. Let's go to Word. Okay. Let me just pull this down. Whoop. There. Okay. So Bayesian statistics, or Bayes theory, or theorem that we work on in this chapter, turns out to be an incredibly powerful tool of statistics, or a way to think about statistics. And it's not as intuitive as it seems. And the reason we know this is that we sometimes test people as to how well they do with this type of kind of mental calculation. I don't want to misattribute this, but I believe it's in Daniel Kahneman's Thinking Fast and Slow, where he outlines or talks about a test of physicians. So this type of Bayesian statistics, or Bayes theorem, you'll see is pretty useful for medical diagnostics, or thinking about how likely certain outcomes are. And your book walks through a disease example, and we're going to do one here as well. And so what I want to preface this by is saying that we're all pretty bad at this, even people that deal with these realities quite often in the terms of MDs and positive tests for cancer screenings, or other disease screenings. So it's a pretty powerful way to frame our likelihood of certain outcomes when we learn new information. Okay, so really what the heart of Bayes' theorem is, we have prior probabilities or thoughts on the likelihood of certain outcomes. We get new information. And so what do we do with that new information? And of course, this leads us to conditional probabilities, right? Because in many ways, that conditional probabilities are new information. How do we handle a certain probability given that something else has occurred? And in as we'll see here, given that perhaps you get a positive test result. We're going to just walk through this example, and then we'll turn and talk a little bit about where we are, and how this applies to some of the testing and numbers that have come out over the last number of months, and how this relates to COVID testing and large sample testing. Okay, so the scenario I have set up here is one that is, again, not that different, or not that rare for medical situations, right? So in medicine, or in life, we have a lot of diseases or afflictions that impact a small percentage of us overall, but because there are so many of us, it ends up that a lot of us, or a large number, have a certain disease. Okay, and so for instance, there are certain types of cancer, not for all of us, or well, all of you, but 1% of people having a certain type of cancer we don't have a cancer that 1% of the whole population has, but we do have cancers where, you know, if you're a 50-year-old male, I haven't looked up these numbers, but it's probably not wildly different than 1% of, you know, 50-year-old or older men having prostate cancer, for instance. That's why eventually it's, you know, you're supposed to get your prostate exam every however many years, or colon cancer or something like that. Okay, so this is not an outlandish situation. And then we have certain tests for those diseases. Okay, and oftentimes the initial test is not designed to be perfect. Okay, we have simple tests. Maybe it's a colonoscopy, and you see it may show up some whatever cysts or I don't know what they're called. But it's not rare for something an initial test to have something like we outline here, where if you have this cancer, there's an 80% chance that it'll be detected by a test. That means 20% won't be detected. Okay, and then the other side of it is if you don't have this cancer, there's a certain chance that you will still test positive. So here I have listed just as 9.6% chance. So even if you don't have it, you might still get tested positive. And you will then on the flip side, right, if you take the test, you have a certain chance to test negative. So some of this might sound familiar. And depending on the literature that you're in, you'll hear it referred to as false positives, false negatives, right? So that pops up a lot in regards to COVID testing. You might also have heard of it as type 1 and type 2 error. Okay, and we'll circle back to type 1 and type 2 error later on in the semester. But this is a form of it. You also will hear it in medicine, if you're interested in medicine, or you're kind of pre-med or I don't know, in anatomy or something, you might hear it referred to as the specificity and the there's another word. I'm not in medicine. Specificity and the I'll think of it in a couple minutes. So there are different ways to reference these same type of concepts. But what we're interested in here is, let's say you go in for a test, and this happens to a lot of people. They go in for a cancer screening, or you find a lump somewhere and you go in and get a test, and it might have these similar percentages. What is your likelihood before the test of having the disease, and what's your likelihood after the test? Or let's say it's just a routine screening. Okay, so I become 50 years old and I need to go get my yearly colonoscopy or something. I should look up when I'm supposed to start that. But let's say we do that, okay? Or this is a new type of cancer comes out. I'm trying to make this applicable to 20-year-olds. You don't have the cancer scares in general. So what Bayes' theorem does is breaks it down into prior probabilities and posterior probabilities. Okay, so prior probabilities meaning before we have any given, we don't know what happened on a certain exam. Okay, so just in general, our prior probability is, let's see, where am I? So the prior probability, that's behind the screen, is going to be, what's the probability, and notationally, I'm going to call this A1. Okay, I'm going to consider A1 just to match the book outline. I'm going to consider this, though, the probability of having cancer. Okay, so oftentimes when you're working through a complex problem like this, it's good to write down kind of what our notations mean. So probability of A1 means the probability of having cancer. And so we can think of the probability of A2 as the probability of no cancer. Okay, and so so we can quickly answer that question, right? So before we go in and get the random screening, our probability of having the cancer, if we're just one of the random people in the society, is simply 1%. Okay, so I can find where I am here. Our priors, or a prior probability is the probability of A1 is simply 1%, 0.1. Okay, so without any other information, we think there's a 1% chance. Our probability of not having cancer then, because these are only two options, is 99%. Okay, but you might go in and take the test and you get the phone call from your doctor and it says you tested positive for the cancer. Okay, obviously should be a scary phone call, and it is, but what is the actual probability that you have cancer, even or given that you've tested positive, right? And so we know how to write this out just from our discussion of conditional probabilities. So what's the probability of A1 given that you test positive? Okay, I'm just going to write testing positive as B. Again, just to match up the kind of the book formula. And rather than having to rewrite everything out and keep writing given that you tested positive, we'll just shorthand it there. So maybe I'll just make note. So the probability of B is probability tested positive. Okay, just to remind ourselves that that's what we're dealing with. So the factor that, or the probability that we're now interested in is, what is the probability that you have cancer given a positive test? Okay, you got the phone call. How worried should you be? Well, as we'll see, this is going to depend on a lot of the numbers that we have laid out here. So I'm going to write down the formula. Let's see if I can give myself a little more space. Not going to help. Okay, so the formula that we're going to work with is, actually, let me grab this. Remind ourselves of what we're dealing with. I'm going to try to shrink that, but maybe we'll just have to refer to it. Okay, so the probability, what we're interested in here is the probability of A1 given B. Okay, and what is that? That is the probability of cancer given that we test positive. Okay, so that, it turns out, and we'll talk about some of why this is the case, but that is equivalent to the probability of A1. Okay, so the probability that randomly you had cancer, or your prior probability, right? So the probability that any person had the cancer, times the probability of B given A1. Okay, this is not the same as what we're looking for, right? This is the reverse. We're interested in the probability of cancer given the positive test, but one thing we can use is, what's the chance or the probability that you get a positive test given that you had cancer? Okay, and we know that information, so we'll come back to that in a moment. To finish out the equation, we on the denominator, we also have the probability of A1, probability of B given A1. Okay, so that's the same. Try to give myself more space here. And then plus the probability of A2. Now remember what A2 is. It's the probability you don't have cancer times the probability of a positive test given that you don't in fact have cancer. Okay, Now, you can go deep into the weeds, and we'll talk a little bit about why this math is working. But in some sense, we can use this tool even if we don't fully understand what's happening. But once we get some numbers down, I think it'll be a little more clear. So a lot going on, but realize these are all probabilities or conditional probabilities, and we have all of that up here. All of that is contained in this little blurb here. If I've done this right, there's a chance I messed up the question. Always a chance. Okay, so all of this junk here up above, we know the information too. So we do not know the probability of cancer given a positive test, but we do know things like, if you have cancer, what's the chance that you test positive, right? That is an 80% chance. So things we need to know, I'm gonna have to move myself here. Things we need to find out. The probability, let me just change colors to make sure we can see the probability. What's the probability of, we know A1, but let's just write that down. We need the probability of A1. We need the probability of B given A1. Okay, always good to kind of organize your thoughts. The probability, what do we need? We need A2, and we need the, close that bracket, and we need the probability of B given A2. Okay, so those are the only four objects that show up here, right? So we have A1, probability of B given A1, that repeats, and then we have A2 and the probability of B given A2. So if we know these four things, we can figure out how scared you should be. Okay, so what's the probability of A1? This is our prior probability, right? It's one of our priors. That is that 0.01. Okay, similarly, we know that this is 0.99. Right? That was our prior probability of not having cancer. Now, the only two left to plug in are based on the testing, right? So, of course, this is going to change depending on the quality of the test. But here, let's see, what's the probability that you test positive given A1, given that you have cancer? So that's in our second bullet point or second dash. If you have cancer, 80% it'll be detected. Okay, so this is 0.8. And then what if you don't have cancer? There's still a chance that you show up as a positive, right? That would be a false positive, but still a chance. And so we have 9.6%, so 0.096. Okay, so now we have our four missing pieces here. And trying to think of how I want to. I want to have some space here is what I really want. So let's just get rid of that. And we'll just do that in this window here. Okay, I'm gonna come on over here. All right, so let's rework this formula, but plugging in what we know. Okay, so the probability, switch colors again. The probability of A1 given B, and that's what we're after. And now let's plug in, we have so probability of A1, we have 0.01 times probability of B given A1 is, we can look at that, that's 0.80, so 80%, right? Another benefit of an exam being open book, open note is that you don't have to try to memorize all of this. As you can see, I have to always refer. Okay, so the probability of A1 again. So here we're just repeating. Okay, and then plus the other kind of option here is probability of A2, so 0.99, and then this is 0.096. Okay, so now that we have some numbers put in here, before we crunch it, let's talk about what's going on. So imagine we have a lot of people, right? Maybe we have 1,000 people that are all going to go in and get tested. Some of those people are going to have cancer, okay, or the cancer that we're screening for. And in fact, if 1% of the people have it, so if we had, just as kind of to sketch out what's happening here, if we had 1,000 people, 1% of that is 10 people. So there are probably, on average, there are 10 people in this 1,000 that have cancer. Those 10 people are going to get tested because we're testing all 1,000 people. Only 8 of them are going to flag as positive, right? 80% of them. So what we're calculating here is kind of how many are going to get flagged as positive that are positive, and then we're going to compare it to the total number that are going to be flagged as positive, which is going to include those 8 that get flagged as positive, but it's also going to include the members, the healthy, that get the false positive or get positive positive test even though they're not positive. Okay, so this is what Bayes' theorem lets us do. So just to reiterate, that's 990 people, all of which are healthy, but they have a 9.6% chance of flagging as having cancer. Okay, so that's going to be a lot of people. Even 10% of roughly 10%, that's 99 people or something like that. Okay, so it's going to be a lot of people that show up as positive without actually having had having had cancer. So that's really the balance that we're striking here, or we're comparing. And so we can crunch that number. If you do that, you get. Let me just write it down. If you do all this math, you get something like 0.0776, or just to make it more confusing, over here, 7.6% chance. Okay, so the probability of A1, so having cancer given you get a positive test, is 0.0776, or 7.6%. Okay, so you should, that's off the screen. You should be concerned, but you should not assume that you for sure have cancer when you get the positive call from your doctor. Okay, so I started this by saying, we're all pretty bad at making this calculation. In fact, doctors perform, actually, I think the study showed that doctors perform even slightly worse than general people at trying to say, they give them some of these types of numbers and say, okay, what do you think the likelihood that the patient actually has the disease is? And I think our default, and I think the study showed this, is that people would say, something like 80% or something. When in reality, it's more, in the 7%. Now, again, this is highly dependent on the numbers that we chose here. So, if we had a more effective test, or a more if the 80% was 95% and the 9.6 was 2% or something, that would lead us to a more, we'd be more certain that we had the cancer here, although still not that high of a number. It might be more of 30% or 40%. Okay, so why is this important? And why is this type of thinking important? Well, as we saw, or as we're seeing with COVID-related situations, this has kind of direct implications. And that is, for a long time here, for 6-7 months, we've been trying to get a hold of, or a grasp on, how deadly COVID is. And part of that is based on how many people have the disease, right? And so when we think about calculating things like infection fatality rate, right? So the how many people die based on how many people, or compared to how many people get the disease. We do need to know how many people got the disease, and that's quite hard to find when we don't have adequate testing, right? And we're not doing large scale testing. And so one way to think about this, and as we turn to going back into sampling, right? And so we'll get to that in a few chapters. But remember, back from chapter 1, we talked about sampling and versus the population and the concept of biased. And so we do have this struggle with our numbers in that a lot of the information that we have, a lot of the testing we have, is from people that are concerned or have reason to believe they might have the test or might have the disease. And so what that's led us to miss out on are some of the either asymptomatic or pre-symptomatic patients or people with very mild symptoms that didn't feel necessary to go get testing. So figuring out how many people have had the illness or have had the virus is a difficult question. That can be overcome with random sampling. So if we were to, and still would be a good idea to do, is to do some broad-based random sampling. Again, we'll turn to this more in later chapters and talk about the math of why this is the case. But if we were to do some of that testing, we'd get a better feel for how widespread the disease is. We have had some instances where we've done some random testing or a closer approximation to random testing. There are some cases or some situations in Indiana. In some sense, we can get there were some early situations in New York that were close to kind of random sampling. But one of the things that this Bayes theorem highlights is that a lot of what we think as far as the prevalence of a disease out and amongst us is based on the issue of false positives and false negatives. Okay, and so when we have large groups, we can see that these percentages don't line up perfectly. And so I don't know how attuned to the various ups and downs of the news cycle and COVID-related information are, but you may recall from a few months ago some buzz about trying to figure out how many people have had it thus far, and there'd be some studies come out that say, okay, maybe it's 10 times as prevalent as we thought it was. And so maybe 13 or 23% or something have had the disease. And what a lot of those calculations were failing on was this understanding of what happens when you have false positives. And especially with regards to large numbers, okay? And so if the prevalence in society is quite low, you're going to have a large share of false positives. And that's what we see here with in some sense, this scenario is not far from COVID-related situations in that if we were to randomly test everyone, because even at this point, maybe 10% or 8% or something have had the disease, we still would get large numbers of these healthy people that flag as being positive. Again, not to these extremes, but we do have to make these adjustments in our calculations. So Bayes' theorem and Bayes statistics or Bayesian statistics is a tool and a way of thinking that is quite important at this point. With regard to COVID and our understanding of caseloads and infection loads and infection fatalities. So just in the last few minutes here, I want to turn. I have a couple other questions on this, which feel free to peruse through. In fact, we didn't get to this, but we could also calculate the probability of, let's say you test negative. How sure are you that you're negative, right? We can rerun this Bayes theorem, altering. So I have A1 written here, right? But you could rework it using A2, right? So or A1 given a negative result. Okay, so the information in this question, we could rerun this and say, you get the phone call, it's negative. Can you rest easy? Are you pretty sure that you don't have cancer? And so you can feel free to kind of rework this and maybe just as an example or as a final bow on this discussion, if we were in that case we're worried about or we're interested in, let's say, so what is the probability of actually having cancer given that it's a negative test? Okay, we'll just call that n. But we would have to then rework based on still these same numbers, right? But we could rework and say, okay, what's the probability of a negative test given that you have cancer, right? And what's the probability of a negative test given that you don't have cancer? Okay, and these are still contained in here because what's the probability of a negative test given that you have cancer? We know that it's 0.2, and then this one is 90 or 0.904, right? So we could then calculate this answer by just reworking that formula. Okay, so it might be something you can try on your own. Okay, I want to just end with a little discussion about the importance of things like pivot tables, or the term that we use in the book, not pivot tables. That's what happens when you're up sick during the night. You lose track on words. But so similar. Okay, so how do we get a grasp of the likelihood of certain people or individuals passing away from COVID? Okay, and so we can look at things like pivot tables to get likelihoods, and with that conditional likelihoods or conditional probabilities, right? And so I have some data here, and I think this is from a study out of Spain. Again, I said it's really hard to get total infections, especially when we don't have adequate testing, but certain places have had better luck with that, or not luck, better testing, and so they have we can get a sense as to the infection rates, and so this is a study from Spain, and it's actually back in early June. So again, a rough estimate, but we can, if we lay out the data in this sense, and I have ages here, so ages 0 to 9, 10 to 19, and so on, and we have died and survived and total infected. Okay, so laid out in the tables that we're becoming accustomed to. And I just want to highlight that, again, these tables have, they contain a lot of information for us. And we have the original frequency tables, right? So forget all the age stuff. We have just the, oops, not even close. Oh boy. We have the total. We can just do, if we're just curious about what is the overall infection fatality rate. To find a way to figure out where I am on the screen. Infection fatality rate, right? So if you become infected, what's your chance of survival? Again, this is independent of your age. So in that case, we just simply do 27121. Again, this is out of Spain, so why it's not 200,000 or something. And we would then divide by the total number of infections, right? So a simple probability based on empirical data as best we can get. And again, oftentimes empirical data, we have these caveats that we're trying the best we can. And let me just plug that in. Actually, I think I have it listed somewhere. I think I have it. So that comes out somewhere in the 1.11 1.1% or something. Okay, so again, an early estimate. We might in general have slightly different estimates, and in fact our ability to treat has done a little better, so I would guess most estimates have it lower than that nowadays. But what I want to highlight is that we can also zoom in here and think about age specific IFRs, or really what we're talking about is conditional probabilities. So this is the probability of survival, so probability, well, not the probability of survival, it's a probability of death. But we might be interested in probability of death given a certain age group. Right? So if you have a loved one that's 40 to 49, for instance, you might be more concerned about that infection fatality ratio. Now, again, this is just based on age. We're not taking into account other issues they might have that are going to also, we could update this further, right? So we've only talked about conditional probabilities based on one item so far, but we could say, and this is feasible and beyond what we're going to calculate in this class, but you could have the probability of death given age 40 to 49 and a smoker and obese. Okay, so those are calculations you can make as well. And if you think about kind of the pivot table, it's less clear, but you could add in extra kind of subgroups and find that data as well. Anyway, if we're curious just about this, again, we're going to ignore, we're only going to look at kind of this, and I wish I could cross out, but we're only going to look at kind of in between these, just at the 40 to 49. So we have 287 divided by the total 447,942, right? And that's going to give us something. It should be 0.064% or something. I'm completely behind. It's behind me. Okay, so my point is here, another or more practical reason you might want to look at a pivot table or contingency table. You know, we know who died on the Titanic, but here we don't. And yeah, more pressing determinations. So this is one of the ways we come up with those age-specific fatality percentages. Yeah, and so you may hear a lot of talk about age-related situations. So I realize we're running over time, but I just wanted to highlight where we are and why we use some of those methods or tools. So we'll end there, and I'll stick on here for a little bit if people have questions. Otherwise, remember I do have office hours here in another hour. So feel free to swing in there.